Hello everyone, welcome to a new video. In this session, we're gonna talk about data reduction strategies. So when we are trying to do some machine learning, create models, either for prediction or pattern recognition, sometimes we face, a large volume of data, and there are different strategies to deal with this problem. So I'm sure that most of you are familiar with dimensionality reduction strategies. So what is dimensionality reduction? That's when you when you want to reduce the number of variables or features in your dataset. So let's say that you have from x1 up to xk variables, and there are some strategies to take a subset of these features, right? So we decrease the dimensionality in our dataset. What we're doing in dimensionality reduction is to remove some columns, right? Now, in the case of data reduction, which is the focus of this lecture, so we are not removing columns here. We're going to try to remove some rows. Not just rows, I'm talking about tables, but it's also, let's say, for video, if your data is about videos. So it's possible in data reduction just to take a subset, the sample of the video, where like the most interesting part of your analysis, should be focused. So the strategy that you're going to learn in this video, it's about data reduction, not dimensionality reduction, that you have discussed even in other courses in our master program. Okay, so why data reduction it's important? Well, because it's going to help you to save storage, computation, and latency, so resources, right? Remember that in general, we have limited resources, so we need to be smart in how we use them. Okay, so why data reduction matters? So you are aware at this point in this course, remember the 5 Bs. So there's volume and velocity. So we're capturing a lot of data. So there's a data explosion. And therefore we need to, find strategies or ways to handle these large volumes of data. So in the case of sensors, for example, IoT, it's very common that the sensor, they capture a lot of information, even per second or less than that. Therefore, after a large period of time, you have accumulated a lot of information, but sometimes you don't need all of that information. You just need some part of the information. So you can summarize it, or you can, identify ways to get what you really need in order to make a prediction or identifying a pattern. So there is a cost, of course. So the more data you have, so there will be more complexity involved in your analysis, the storage, the network, the computational time. In some cases, you will need to split the data in different packages for the storage and even for the computing part. So that requires more like technical skills, and you also need the infrastructure to do that. So what are the goals in data reduction? Basically, we want to keep essential information. That's the most important part. And we want to discard the redundancy, like all the information that we don't need. So this is our focus right now, to ensure that we get, the most important part of the information. So the first strategy, and I'm pretty sure that you have talked about this before, it's sampling methods. So instead of using the complete data set, you can take a subset of the records. That's very common, like in real life when there is going to be a poll, like a survey, you're conducting a poll, typically you won't get access to the complete population. So you need to draw a sample from the population. During the election, election, during the presidential races, it's very common, like with all the polls. So, and if you check the sample size of the polls, it's small, like 2,000 people, 3,000. And they are representing, like millions of, a population of millions of people, because they're using sampling techniques. Now, there are different sampling strategies. So the focus here, or the point, is that you don't always need to use every single piece of information that you have. It's fine. I mean, if you have a small data set, that's fine. But if you have a very large data set, you can be smart about the observations that you get. So it is possible to draw a representative sample. So let's check the different sampling methods, and we will go over two case studies to to understand how they work. So the first one, which is not in this picture, is the convenience sampling. Convenience sampling is not a random sampling. Convenience sampling is just like when you survey or when you take observations that are easy or that are like very accessible. That's very common, for example, when you're doing a homework and you need to collect a survey from, let's say, 20 people, and it's not relevant, like the you don't have to be very strict in that specific context about the sample selection. So you can, just interview some friends, family, and that's a convenience sampling, which is fine when something is informal. But if you want to generalize, make an important inference, then the convenience sampling is not an option. So the first type of sampling is the random sampling. The idea here is that every single observation or individual, they have the same probability of being selected in the sample. So they have, like you can pick any of them and you will pick them randomly. There is no like a pattern in the way in which you draw the sample. And again, every single observation will have the same probability of being selected. So that's the random sampling. So when the random sampling works, is if your data set or if the population is homogeneous, it means that like it looks similar in general. So the random sampling is fine in that specific case. Now, what are other strategies? This one, the systematic sampling, it's kind of like the random sampling. The idea here is like you fix like a k, let's say k equal to 3 or 2, and then every 3 observations, you pick that observation for your sample. You draw it, for your sample. That's a systematic sampling. It's not special. It's just a way to do the random sampling. Now this one, it's more useful, or at least when you have a population or a data set that is heterogeneous, that like the observations are different, you have diversity, they have different variables, then the random sampling is recommended and you will need a stratified sampling. Let me give you an example when stratified makes sense. Let's say that we're doing like a market research about a new product or service that a company wants to offer. And okay, you wanna, like interview some people to check their preferences. Now, if the product or service is for the like upscale market, it's very expensive, then maybe a critical variable here is the income, right? So you need to stratify per income because most likely that variable is going to be relevant. It's going to be relevant because for sure, if the product is expensive, it will define like whether like people is going to be interested or not. So in that specific case, the income makes sense. In our case study that we will check soon in the video, we are talking about a restaurant that is going to open. Now, in that context, maybe it's really important to know like if the person has a family, if they have kids, to be more specific. Why it's important? Let me talk about my my personal experience. I have two kids, so for me it's relevant when I'm going like out to have dinner. For me it's relevant whether the place has a like a small park, something like that for the kids. Also, if there is like a menu for the kids, that for me it's important, right? So depending on the context, there will be some variables that will help you to stratify. So the stratify means that you need to represent the sample in a similar way to the population. Now, how you do that? So you need to find a percentage of how, like, for example, family with kids. So you need, if that's a variable, whether a family has a kid or not, has kids or not. So you can find, okay, like in my data, in my population, let's say like 40% of the families, they have a kid, and 60% they don't have kids, right? So when you're doing the sample, this is the population. So when you're doing the sample and it's a stratified sample, you want to ensure that in the sample, you also have these 40 and 60. meaning that 40% of the families here, they have kids and 60% they don't have kids. So the sample looks similar to the population. In the random sampling, you cannot ensure that. You're just picking, people randomly. But here in the stratified sampling, you try to ensure that a variable of interest, in this case, like whether the family has kids or not, is represented exactly in the same way as the population. So that's the interpretation of the stratified sampling. Cluster sampling is similar, but in some cases, your population, like it's spread geographically speaking. Even in a city, there will be like different, neighborhoods. So you can create some clusters. The idea is that these clusters, they look similar to each other. Now, you will focus only on some of the clusters, not all of them, and you will draw the sample from the clusters, and you can do a stratified sampling in the clusters. Why you will do cluster sampling? The thing is that these percentages are unknown in general. You know, for a variable, you know the universe, you know the population. What is this exact percentage? But now maybe for a cluster or just for a small portion, you can find that percentage. You can do like an estimation. So once you do that, then you perform the stratified sampling. So the cluster sampling is when you have unknown, when the distribution of the variables is unknown. Okay, let's go over the examples. The first one is just a random sampling. I'm pretty sure that you have seen it before, the A/B testing. So this is very common in websites when you want to compare two or more changes or variants. So the idea of the A/B testing is to perform an experiment, a randomized experiment, and you want to see whether option A or option B is better. So in this specific case study, it's for a university, Montana State University. It's a popular A/B case study. So in their case, this is their website at that time. That was like more than 10 years ago. So they had three links: find, request, and interact. That was the original, website. Now, they in their experiment, they were trying to see alternatives for the interact link. So instead of using this, they were trying different labels. So what were the options? So the control case, which is the original state, is interact. And now the alternatives were connect, learn, help, and services. So there were 4 variants: the control and 4 variants. So with the A/B testing, what they did is, they created the different versions, the control and the different variants, right? And now, at that time when a user was going to their website randomly, so they were using just, like a simple random sampling, they assign that user to one of the variants or even the control. So this is a multi-branch experiment. It's not the traditional A/B testing where there are 2 options. It's multi-branch because there are 4 variants. The metric of performance for them was the click-through rate. So what is the idea of the click-through rate? Let's say that 500 users go to the website, but only 20 users click, in that specific link. Then in that specific case, the click-through rate will be 4%. Okay, so they started their experiment in 2013 during 3 weeks, and they started analyzing each, the control and the different variants. So this is the first one, the control, the interact. So the click-through rate was 1.8%. This is the heat map for that scenario. It's nice. So in this specific case, you notice most of the users, they were to find. So that's why you see the colors here in find, right? Now this is variant number 1, same idea. They analyze, and the click-through rate here for variant number 1, the connect was 3.6, was higher. It was higher. This is the heat map for that case. Now, same idea with the other variants with learn, help, and services. So they try, like the 4 variances and the control. And then this is the summary of the data. So the click-through rate per group or per sample, right? So the control group, the click-through rate was 1.8%. But if you notice, there are 2 variants that the performance was twice the control group. For example, Connect, the click-through rate is 3.6%, and Services is 3.5%. So these two look like good strategies, right? Or alternatives compared to the original one. So using just simple random sampling, they were able to identify good candidates, right? So this is very common in websites where they have alternatives and they present different alternatives to the users, and you don't know that because when you open the website, you just see, like the version that you get. Now, this is not enough. It's not by looking at the numbers and you will say, oh, this one is better. Remember, if you want to confirm which one is better, you will need like a statistical analysis, hypothesis testing to see if the difference is statistically significant or not. Okay, so this is our first example. Let me show you the second example. So in this one, this is for a restaurant, a small sandwich shop, and they are gonna open, but they are, like designing the menu, and they wanna know, the preferences of people that live close to the restaurant, to the sandwich shop. Now, what are the questions? Okay, they are asking questions about the type of meat or veggie that like people prefer in the area: steak, roasted veggies, chicken, ham. Also the cheese, provolone, cheddar, all the options, the type of bread, whether they prefer to go out for lunch or for dinner, the preference for dessert, day of the week where they prefer to eat out, if it's during weekdays or weekends. So these were like the 6 questions. So all this information was generated randomly. You will find the file on Brightspace with information. But again, it was generated randomly. It's not real data. It's synthetic data. Okay, so the idea of this problem is just to compare the different sampling strategies. Okay, this is how the dataset looks. So this is only like one person. So the building is where the person lives. There are only like 4 buildings or blocks if you want. Number of kids, if the person crosses the corner or not. The income quartile is relevant here. The dessert preference: ice cream, cheesecake, apple pie. There are 4 options. If they prefer weekday or weekend, lunch or dinner, the type of meat, cheese, and bread. So these are the variables. They are explained here in case you wanna, like read the details. So the first one is convenience sampling. So for convenience sampling, we draw a sample from the data set. This is not randomly. And then we analyze for that sample. This is a sample of 100 people. Using convenience sampling, we analyze their preferences. So this is for dessert, they prefer cheesecake. Weekdays, weekend, they prefer weekend. Like same thing with the other variables. Now, this is what I'm doing, what I'm showing here. It's not realistic. This is just more for educational purposes. But what I'm doing here is like I'm collecting like 50 samples of 100 each. It's like I'm repeating the experiment, like 50 times. So in the case of the veggies or the meats, so this is what they prefer in that specific sample using the convenience sampling. So in the first samples, they prefer roasted veggies and chicken, roasted veggies. You see there is variability here, right? Roasted veggies, chicken, there is some variability here, and that's not good. That's not good. That's mainly because this is convenience sampling. Now, let me show you how bad the convenience sampling is in our example. So in the left column, you will have the preferences in the sample, only 100 people. And to the right, you will have the preferences of the population. In general, you don't know this. I mean, this is unknown. In this specific case, because the data set, we generated the data set, therefore we have this information. This is just for educational purposes to compare whether that sampling is a good estimation or not of the population. So in the dessert, for example, in the case of the dessert, please note that for the sample, the preference was cheesecake, but in reality, in the population of the study, is apple pie. So it's missing, right? It's pretty bad. It's very far, very far. You can look at the other variables, but just by knowing the dessert, and you can see that similar things can happen. In the meat, it's close. It's not that bad. In the case of cheese, it's also, let's say, it looks similar. The provolone is the best for the sample, also population, but the second best option is not the same, right? So you see there are some discrepancies here. There are differences. That's because the convenience sampling is not a good way to carry out the sampling. So let's see now the simple random sampling. So here, every single individual will have the same probability of being selected. In our dataset, we have 100,000 observations, and we're going to get 100 from this. So we carry out the same idea, like we collect our sample and we analyze their preferences. Apple pie, roasted veggies. And here again, now we repeat the experiment, in this case, 200 times. It's like we collect 100 samples 200 times just to see. This is for the cheese, for example, if it changes the preference. Have you noticed it's changing? This is not good. It means like if you're using the simple random sampling in this specific example, every time you get a sample of 100, the preference of the cheese changes. It's like you have this is the variability that is shown here. Like in some samples, cheddar is going to be the preference. In other cases, provolone. In other cases, double cream. In other cases, the Swiss. And that's not good. You don't want that variability. You want something more consistent. So that's one of the problems with our sampling here. We can increase, maybe a possible solution is to increase the sample size. So instead of using 100, let's use 5,000, for example. So again, here we repeat, okay, the experiment. We collect 200 samples of 5,000 each. And the variability is reduced. Please note that the double cream option is removed. So now that you have a bigger sample size, 5,000, now the less preferred option in the case of the cheese is not shown here, which makes sense. Which makes sense because now that you have a larger sample size, then you are getting more information about the population. So your estimation it's improving, but you still have here variability because in some samples, Swiss is going to be the best option. In others, cheddar is going to be the best option. So this shows that there is heterogeneity in our data set. It's not homogeneous. So a good idea may be to try some stratified sampling. So here we have some variables, candidates, building, kids, income quartile in our data frame. So here for sure, income quartile and kids make sense, whether you have kids or not, or the number of kids and the income quartile. So in the case study, it's easy to get the percentage per variable. It's like the distribution of the variable. So for example, here for building, we know that there are 4 buildings and they are distributed in the same way. 25% of the observations are located in each building. And in the case of kids, it changes. So 15% of the data set has no kids, 25% 1 kid, 45% 2 kids, almost 10% 3 kids, 5% 4 kids. That's the distribution of each variable. So it's not homogeneous. If you check at the kids, it's not homogeneous, right? It's not like a uniform distribution. Okay, same idea or similar idea with the quartiles. So let's draw samples, but now when we draw a sample, let's try to keep this percentage, this distribution. So let's say If you do a stratified sampling and using the kids variable, it means that in the sample, you need to ensure that you have individuals with 0 kids, 15%, approximately 15%, and then 25% of individuals in your sample with only 1 kid, 45% with 2 kids. Like that's the idea of the stratified sampling, that your sample looks similar to the population. It has the same distribution in some of the variables. In this case, kids or income quartile, it depends which variable you pick. So here we create a function. We define a function that uses the data frame, the sample size, and which filter you're going to use for the stratified sampling. So now when we perform when we check the preferences with this per building, and this is for kids. So please notice that apple pie is preferred, which is consistent with the population. This is we use income for the stratification. We're using one variable at the time for stratification. We're not mixing the variables. It is possible, but here we're applying just one at a time. Okay, so now let's see the most popular dessert if we perform the experiment multiple times. So please notice how we're decreasing the variability here. So for the dessert, in the 200 experiments, when you were drawing samples of 100 people using a stratified sampling. So this is for the case of the building. Apple pie was the winner with the kids. Please note apple pie was the winner, but please notice how small is the variability compared to the previous sampling strategies, where they were more like they had a different distribution here. So now what you notice is that this is more consistent with the population. So you're getting better estimations. Okay, I'm gonna stop the case study. Let's continue, because you get the idea, right, on how these strategies work. People in general, when they think about, okay, let's draw a sample, the first option is just simple random sampling. Just like, okay, every single observation has the same probability. That's fine if your population is homogeneous, but if it's not, like in this specific case study, then you will need to perform, some stratified sampling, which is kind of like the gold standard when you are drawing a sample. Okay, there are more strategies for data reduction. The first one was sampling. The second one, filtering and pruning. So the idea here is to remove relevant data. So let me show you this case study. This is for the Disney parks, Magic Kingdom and the other parks. So they were having issues with some people getting into the park without paying the ticket. They were breaking in, and of course that was a problem for them. Now, what was the challenge here? The challenge is that this is video. They were having information from different cameras, and there was a team of people reviewing the video, but the amount of data was too much. It was very difficult to keep track of too many cameras, too many hours of video, and the team it was just too much work for them. So they hired some consultants to try to use machine learning, and the consultants were trying to initially they were trying to classify, using videos in real time. They were trying to classify whether a person was like breaking in the park without paying, or if it was a normal entrance to a park. What they notice is that the problem is challenging, not just because it is video. It's because there are so many ways in which one person can get into a park without paying. Like there are different strategies. So there is a lot of variability. It was challenging to get a model with high accuracy. But what they noticed is that it was possible and it was easier for them to detect anomalies, even though they were not able to say, oh, this guy is breaking right now, but at least they were able to say, at this specific moment, in the video, there is something weird. There is something that you should pay attention. Look closely because most likely there is something that is happening right now. So just by using a anomaly detection model, they were able to filter the data. So instead of using, like the full footage, they were able to discard more than 90% of the data, and they just focus, on that 10% or less than that in some cases of the data or the video where there was something anomal, where there was something atypical, something different, something weird. So in that case, then the humans or the team was given that footage, and they were able to identify whether someone was breaking in or not. So they were able to simplify, the workload, and now they were focusing on the relevant stuff. So this is a data reduction strategy. Another example of this, if you have cameras at home, in my case, I have a lot of cameras at home, just to keep an eye on my kids. So nowadays, cameras, they have they did some sensors, and they detect if there is movement. Like if someone is moving, they detect activity, right, in the different rooms. So if you are checking at the video that is recorded, you can see there is like a mark, like in which specific part of the video there was some movement, or like the sensor detected something. So you don't need to watch the whole thing. You can just go directly to that specific sections. So that's an example of filtering right there. It's detecting something, anomalies or movements, depends on the context, of course. And the idea is to focus on the anomalies and discard what is normal. So this is an example of data reduction that will help you to remove a large portions of data, and for you to focus only on the normal part. This belongs to what is called the haystack principle. Remember, you're trying to find a needle in the haystack. So we're reducing the size of the haystack in such a way that finding the needle is inevitable. It's going to happen because we're removing, like most of the noise and focusing on the important part. The last strategy that we're going to cover in this video is summarization. So you're familiar with summaries, and with LLMs, I'm sure that you have used, summaries. You have a large text, a document, and you try to find a summary, whether it's a paper or a book. It's very common, right? LLMs will help you with summaries, but also if you have tables, that's very common. For example, sensors, they collect a lot of data per second, even per millisecond. And sometimes that's just too much. You don't need that detail of data. So you need to compute metrics in some cases. For example, a traffic sensor, it can store the car store the information of every single car, but maybe that's not what you need. Maybe what you need is just, compute the hourly average speed. Maybe this is a more important variable in your analysis, right? So the idea of summaries is not just to summarize text, is to take raw data and replace it with summaries using metrics such as the average, the minimum value, the maximum value, variability metrics, percentile information, in such a way that we reduce the number of rows in our dataset. That's very common also with customers. If I have a data set of my customers, it is possible that I have a lot of transactions per customer, but maybe a single transaction is not meaningful. But if I aggregate the transactions per customer and I compute some metrics like number of transactions, number of items per order, average number of items per order, like average time between different orders, so you can get some meaningful metrics that will help you to really get insights from your data. So you don't. The point here is that you don't need to use the complete data set always. Sometimes you can remove some parts, or sometimes you can summarize in some more meaningful or insightful metrics. That's the message. So just to summarize, just the study that we discussed, but let's summarize our lecture today. So data reduction is essential to handle large-scale data sets. And remember, it's not the same as dimensionality reduction, right? Of course, in both cases, we reduce the size of our data, right? But here I'm focusing, again, I'm not removing features. I'm just removing rows, right, or parts of the data. So filtering removes irrelevant data so we can focus on what is important. Sampling strategies are also very helpful. We can use them to draw a small sample, but that is representative of our complete data set. Summarization helps us to compress our data, right? And we can also get more, insights from our data by computing some metrics. It's very related. Actually, this summarization, in some cases, it relates to feature engineering. Okay, so together these strategies will help us to handle big data and be able to perform machine learning, which is what I want to teach you in this course. Different approaches, different strategies to be able to handle big data, right? So I'll see you in our next video.